Greetings A-level chemists, welcome to today's video where we're going to be looking at required practical 12 of the AQA specification, and we're going to be looking at TLC, thin layer chromatography, but this applies to all exam boards, so Edexcel and OCR-A, because chromatography doesn't adhere to one particular exam board. So let's have a look at the question. So we've got a protein which can be broken down into its component amino acids using an enzyme. So the student's plan is to use TLC to determine which amino acids are present in this protein. And they identified two of the amino acids as alanine and serine. Okay, great. So there's alanine and there's serine. So we've got to use the figure to calculate the RF value of the unknown amino acid. And then we've got to show our working. Cool. And then using that, we've got to determine what the unknown amino acid is. So just going through a little bit of background in TLC. So we'd get a TLC plate or some chromatography paper, what have you, and then we're going to draw a baseline around 1 centimeter up from the bottom of the TLC plate or the chromatography paper. And then using a capillary tube, we're going to blot a spot of the mixture that we're separating on the baseline. And remember that the baseline needs to be drawn in pencil because presumably that's insoluble for the solvents that we're using. And then what we're going to do is we're going to place this in a jar which contains the solvent, and the solvent level needs to be below the baseline, otherwise the spots will just wash off. Okay, and then what we do is we place the TLC plate which contains the solvent and then put a lid over the beaker in which it's contained. Alright, so then what's going to happen, this mixture that we're separating is going to travel up and separate into its components. Now, the distance traveled by the components or the spots depends on the relative attractions that it has to the mobile phase, and that's the movement of the solvent, and the relative attractions to the stationary phase, which in this case is the TLC plate. So what can we say here? Before we answer the question, that serine is most attracted to the stationary phase. The stationary phase is the TLC plate, it's not moving. Whereas alanine has stronger affinity or attractions, to the mobile phase, i.e. the solvent, because it travels further. And then this is the solvent front and it stops here. So what we're going to do is we're going to have a look at the RF values. So remember, we'd allow the TLC plate to dry in a fume cupboard, and these spots are actually colorless. So to actually observe the spots, what we do is we either spray with ninhydrin so that they go purple, or we'd place the plate under a UV lamp which will expose the spots. And then what we do, once exposed to UV light, for example, we draw around the spots so that we know the location of the spots. And then we can calculate the RF values. So if we're calculating the RF values, we're always going from the baseline to the distance of the spot. Okay, so here is my baseline, and let's draw a line up to the unknown amino acid. And I can fix that one a little bit. So it's slightly long, just want to go to the center of the spot. Does that work? Yeah, that's a bit better, he says. That will do. Something like that. Okay, so we've got the distance that the unknown amino acid has traveled from the baseline to its final location, and that's 31 millimeters. Okay, then what we're going to do, we're going to take our ruler and we're going to draw a line from the baseline all the way up to the solvent front. There we go. Done. Okay, so then to determine the RF value, so the RF value, the retention factor, that's going to be the distance traveled by the spot all over the distance traveled by the solvent. That's the distance traveled by the solvent. And now what we're going to do is we're going to substitute our values in, and then we're going to get a number for the RF value for the unknown amino acid. So the unknown amino acid has traveled 31 millimeters. So that is our numerator. And the solvent has traveled 87 millimeters. And that is our denominator. And then what we're going to do is process this. So the millimeters are going to cancel out. So the RF value is, so I get a value of 0.36, rounded up to 2 decimal places, no units here. So you've got to allow for some tolerance in that value. And I think the true value is 0.34 for glycine, but that's probably within the tolerance given by the mark scheme. So we can safely say that the amino acid, AA for amino acid, is glycine. Done. Okay, let's continue. So a follow-up question is, describe how we can make the spots visible at the end of the experiment, because the spots are actually colorless, so we can't see them. So we actually spoke about this, so we could use a UV lamp and then draw a circle around the spots to locate the spots, or we could use an anhydrine, which will make them go purple. Okay, so lots of people say iodine. I think it's probably going to be in the allow section, but it will be allowed, probably. I'd go for these safe bets. UV lamp and anhydrine, we're looking at TLC of proteins or dipeptides, all that sort of jazz. So then explain why each amino has a different RF value. We already spoke about this. So each amino acid has a different attraction or affinity to the mobile phase and the stationary phase. To the stationary phase, which is the TLC plate, and the mobile phase, which is the solvent. Okay, thank you for watching. See you later.